Okay, so we see that the center of mass moves along a straight line. So what should we do? We should choose a coordinate system that is moving with uniform velocity c and the origin at the center of mass. That's a Newtonian frame of reference. So if you do this, the equations will decouple. The 12 equations will break up into two sets of 6 equations each, and the variables are simply related by similarity variables. If you solve one system of differential equations, take the solution, multiply them by a constant, you get the other one. So essentially we have dispensed off with 6 equations, we are only left with 6 more equations, and if we solve this 6 equations, the other 6 can be solved simply by multiplying by a non-zero constant. So the problem reduces to solving 6 equations. This reduction is called reducing the two body problem to an equivalent one body problem. That's the meaning of this, what I have just said. So now, how do we solve these 6 equations? We need 5 first integrals. Now remember that there is no external torque, so angular momentum is conserved, and angular momentum being a vector gives you 3 more first integrals. Total energy is conserved, so that gives you 1 more first integral. Now we are short of 1. We get a total of 10 first integrals. We have a system of 12 equations. We needed 11 first integrals. The divergence of the system is 0. And so a classical theorem of Jacobi in classical mechanics says that one can find 1 more first integral. If we have n minus 2 first integrals and 0 divergence, then we can automatically find 1 more first integral, and we get a full system of first integrals, and the problem can be reduced to a quadrature and an inversion. In other words, the curve that we are looking for, the solution curve, is nailed down, except that the parameterization is unknown. So we are back to the same problem of performing an integration and performing an inversion. What is this equation 8.10 that's going to get inverted in the context of the two body problem? That is the Kepler equation that we are going to now derive. In order to derive the Kepler equation, what we are going to do is we are going to use the Kepler's laws of planetary motion, because the Kepler's laws of planetary motion is basically a consequence of the first integrals. The second law is basically a statement that the angular momentum is conserved. So let us begin by deriving the Kepler equation. For that, let us introduce a few terms. The perihelion. Recall that the perihelion is that point on the orbit of the planet which is closest to the sun, and the point which is farthest from the sun is called the aphelion. So we got the perihelion and the aphelion. Let us call capital pi the perihelion and capital pi prime the aphelion. The sun is at the focus. Let us assume that we are starting the time when the planet crosses the perihelion. The point at which the planet is closest to the sun, at that point of time we start our stopwatch. We begin measuring time from that instant when the planet crosses the perihelion. So when time t equal to 0, the planet is at pi. Now the sun is at the focus f, and now we measure the angles from the vector f pi. We got the vector f pi from the focus to the perihelion. From that initial vector we measure angles. So let xt be the position of the planet at some instant t, and so from the focus we draw fx and we have f pi. The angle between f pi and fx, that angle is theta t, and this theta t is called the true anomaly. This terminology is fixed in astronomy. It's an astronomical term. It's called the true anomaly. So what is the Kepler problem? determine theta t explicitly as a function of time. That is the main problem. So for that we need to get an equation for theta t. Now we have a picture here of an ellipse and its auxiliary circle. Recall the notion of auxiliary circle of an ellipse from your 12th standard coordinate geometry. Suppose x squared by a squared plus y squared by b squared equal to 1 is the ellipse, and the auxiliary circle is x squared by a squared plus y squared by a squared equal to 1, or x squared plus y squared equal to a squared. The circle and the ellipse. The ellipse is completely sitting inside the circle, and the circle and the ellipse touch each other exactly at the ends of the major axis, at pi and at minus pi. Now draw a vertical line cutting the ellipse and the auxiliary circle at P and P prime. The points P and P prime are called corresponding points. So P is a point on the ellipse. Just draw the point lying on the auxiliary circle vertically above if you are in the upper half plane, and vertically below if you are in the lower half plane. They are corresponding points on the ellipse and the circle. So P and P prime are corresponding points of the ellipse and the auxiliary circle. We have area sector pi fp, and that's a sector of the ellipse. P is on the ellipse, F is the focus, and pi is the perihelion. So this is a sector of the ellipse. What about area pi fp prime? F is the focus, pi is the perihelion, and P prime is where? On the auxiliary circle. So it's a sector of the auxiliary circle. So now it's equation 8.11. Area pi fp upon area pi fp prime is the same as the area of the ellipse upon the area of the circle. Now what is the area of the ellipse? Pi ab. What is the area of the circle? Pi a squared. So this ratio is b by a. Exercise: prove equation 8.11 using integral calculus. Use calculus to calculate area of pi fp and the area of pi fp prime. Take the ratio and check that you exactly get b by a, which is also the area of the ellipse upon the area of the circle. Now let us use Kepler's second law of motion. Kepler's second law of planetary motion says that the radius vector sweeps out equal areas in equal intervals of time. So the area swept out by the radius vector joining the sun and the planet bears the same ratio to the time, the epoch through which the planet has traversed. So for example, when time t equal to 0, the planet was at the perihelion, and at time t, the planet has some intermediate position, and it sweeps out area pi fp in time little t. In time capital T, what does it do? It sweeps out the entire ellipse. It has made one complete revolution where t is a period. So what is the area that it sweeps out? The area of the ellipse. So Kepler's second law says that area pi fp upon area of the ellipse is little t by capital T. But equation 8.11 says that this ratio is the same as area pi fp prime upon area of the circle. So we got equation 8.12. So we have used already the Kepler's second law. Now we shall look at the right hand side of 8.12. 8.12, the right hand side concerns a circle x squared plus y squared equal to a squared, and we understand the geometry of the circle very well. So let us calculate those areas. Let us call C the center of the ellipse and the center of the circle. The ellipse and the circle have the same center C, the origin. What happens to area pi fp prime? Area pi fp prime is area pi cp prime minus area triangle fcp prime, you must consult this picture. Over here we have it all. And so we got this equation 8.13. But what is the area of pi c p prime? Everybody knows the area of the sector of a circle is 1/2 a squared phi. And the area triangle FCP prime is half base into height. But the focus, remember, is at AE comma 0. And so half base into height is going to give you a squared epsilon sine phi, where phi is the eccentric angle of P. Remember again from basic coordinate geometry, what is the eccentric angle? The eccentric angle by definition is angle pi c p prime. Pi center C to P prime, the point on the auxiliary circle. That's called the eccentric angle of the point P. So the area of the triangle FCP prime is basically 1/2 a squared epsilon sine phi. That is easy. The sine phi comes from the fact that you have measured the height. A sine phi is the height and the base is A epsilon. So we got this equation 8.14. So substituting 8.14 and 8.12, we get area of pi f p prime upon area of the circle equal to phi minus epsilon sine phi upon 2 pi. And we get phi minus epsilon sine phi equal to 2 pi little t by capital T, using 8.12 again. Equation 8.15 is the famous Kepler equation. This is the equation that we are trying to invert. So now in this equation, the right hand side 2 pi little t by capital T is called the mean anomaly. Again an astronomical term. Phi is the eccentric angle. I already defined for you what the eccentric angle is. There is a simple relationship between the true anomaly theta and the eccentric anomaly phi, and that relationship will be given to you later. So instead of finding the true anomaly as a function of time, we find the eccentric anomaly phi as a function of time. In other words, we invert 8.15 and our job will be done. So for a given value of t, we have to find phi as a function of t. So what is the direct function? The direct function is lambda minus epsilon sine lambda, and the inverse function is the inverse of this, evaluated at 2 pi t by t. So what is the direct function? Lambda minus epsilon sine lambda. When lambda is very large, it goes to plus infinity. When lambda goes to minus infinity, it goes to minus infinity. Lambda minus epsilon sine lambda, it's a continuous function taking arbitrarily large values and arbitrarily small values. So by intermediate value theorem, lambda minus epsilon sine lambda is surjective. It maps onto R. Why is it injective? When is a real valued function injective? Take the derivative. 1 minus epsilon cos lambda. Epsilon is eccentricity of the ellipse. Eccentricity of the ellipse is between 0 and 1. So 1 minus epsilon cos lambda is going to be strictly positive. The derivative is positive, the function is everywhere strictly increasing, so it's injective. So this equation 8.15, the function lambda minus epsilon sine lambda is a bijection from R to R. So there's going to be a unique value of phi which satisfies this equation 8.15. And so equation 8.15 can be inverted to give phi uniquely as a function of t. How do I invert it? The inverse function theorem tells you that the derivative is strictly positive. The inverse function is actually going to be a differentiable function. If the direct function is infinitely differentiable, then the inverse function is also going to be infinitely differentiable as long as it's strictly increasing and bijective. And lambda minus epsilon sine lambda is infinitely differentiable. So the inverse function is also infinitely differentiable. So phi is differentiable as a function of little t infinitely often. So we have proved that the inverse exists and it is smooth. So that is exercise number 1 in this slide. Now explain why the function phi t is an odd function. Use both geometrical reasoning as well as mathematical analysis. I will give you the mathematical analysis argument. The direct function is an odd function and the inverse function is also going to be an odd function. Phi of 0 equal to 0 because it's an odd function. So its value at the origin is 0. Phi of t by 2 equal to pi. Why does this hold? What is t by 2? T by 2 is a half period. So at a half period, where is the planet? At the aphelion. It has started from the perihelion. In capital T is a period. So in half period, it is in the aphelion on the other extreme. But at the perihelion and the aphelion, the point P and the corresponding point of the auxiliary circle, they coincide. P and P prime are corresponding points on the circle and on the ellipse. And when P goes to pi or when P goes to pi prime, these 2 points coalesce and they become one and the same. And so phi of capital T by 2, the eccentric angle and the true angle, the true anomaly and the eccentric anomaly become the same, namely pi. Now the problem of inverting the Kepler equation has been studied by many eminent mathematicians such as Lagrange way back in 1768, and it appears in his Mécanique Analytique. In connection with this, Lagrange discovered the inversion formula that bears his name, which is popularly studied by combinatorists, the Lagrange inversion formula. So now let us look at phi of t plus t. What happens when little t becomes little t plus capital T? Kepler equation gives you phi of t plus capital T minus epsilon sine phi of t plus capital T equal to 2 pi times t plus capital T upon t, which is 2 pi t by t plus 2 pi, which can be rewritten as phi of t plus capital T minus epsilon sine phi of t plus capital T equal to 2 pi little t by capital T has been written as phi t minus epsilon sine phi t. The right hand side is phi t plus 2 pi minus epsilon sine phi t plus 2 pi. So by injectivity of the function lambda minus epsilon sine lambda, we immediately conclude that phi of little t plus capital T equal to phi t plus 2 pi. You can also derive this from physical considerations. Without this mathematics, directly from physics we can derive this. Now using 8.16, we see that if I look at phi t minus 2 pi t by capital T, call the difference psi t. This difference is now going to be periodic. That is very easy to check. Directly check it using 8.16. So now we have got a periodic function with period t. So now psi of little t into capital T upon 2 pi is now periodic with respect to period 2 pi. So now we are in business. And we have got a 2 pi periodic function which is very smooth and an odd function. So what will be the Fourier series? It will only have sine terms, it will not have cosine terms because it's an odd function. So psi of little t into capital T upon 2 pi is summation n from 1 to infinity bn sine nt. So bn equal to 2 upon pi integral 0 to pi psi of tt by 2 pi sine nt dt, which can be written as 2 upon pi integral 0 to pi, put the definition of psi, phi of tt by 2 pi minus t sine nt dt. So now write sine nt as the derivative of cos nt, the minus sign and a 1 upon n in the denominator, and integrate by parts. When you integrate by parts, what happens? We are going to get boundary terms. What are the boundary terms? When t equal to 0, phi of 0 is 0 and little t is also 0. And when little t equal to pi, what happens? We get phi of t by 2. Remember, phi of t by 2 equal to pi. So the other boundary term also cancels out. So the boundary term cancels out, and so the only term that remains is the integral term, where the derivative shifts from the cosine term to the other term with a negative sign. So we get all in all bn equal to 2 upon n pi integral 0 to pi ddt of phi of tt by 2 pi minus t cos nt dt. Now I must carry out the differentiation. I'll get two terms. I will get ddt of the phi term, and derivative of t is 1. But when you integrate cos nt from 0 to pi, I get 0. So the other term disappears. I simply get 2 upon n pi integral 0 to capital T by 2 phi prime s cos 2 pi ns upon capital T ds. I made one more change of variables. The integral from 0 to pi becomes integral from 0 to t by 2. I put tt by 2 pi equal to s, as you can see. So now again let us go back and put the expression for 2 pi little s upon t. 2 pi little s upon t is again using the Kepler equation phi of s minus epsilon sine phi of s, and we get bn equal to 2 upon n pi integral 0 to t by 2 phi prime of s into cosine of n phi s minus n epsilon sine phi s ds. Now we are waiting, make a change of variables, phi prime s ds, that immediately suggests we should put phi of s equal to lambda. What are we going to get? Bn equal to 2 upon n pi integral 0 to pi cos n lambda minus n epsilon sine lambda d lambda. But what is this integral representation? Remember, in the very first module, we derived the integral representation for the Bessel's function. We recognize this integral as the Bessel's function order n. It is exactly Jn of n epsilon. So we have found the Fourier coefficient in terms of the Bessel's function, and we have written down psi of tt by 2 pi, which is phi of tt upon 2 pi minus t, is summation n from 1 to infinity to Jn n epsilon upon n sine nt. The eccentric angle phi t, or the eccentric anomaly, has been expressed as a series 8.7, which is phi of t equal to 2 pi t upon t summation n from 1 to infinity to Jn n epsilon upon n sine 2 pi nt upon capital T, equation 8.7, and that's called the Kempton series. So finally, the problem of expressing the eccentric anomaly as a function of t has been achieved. That is exactly equation 8.7. As I promised, there is a relationship between the true anomaly and the eccentric anomaly, and that relationship is right here on the slide. Tan theta by 2 equal to square root of 1 plus epsilon upon 1 minus epsilon tan phi by 2. Prove this by using elementary trigonometry. So for a short but quick historical survey of these things, see the book by C.A. Ronan, Science, Its History and Development Among World Culture. And there is a very interesting book by J.M. Danby, Celestial Mechanics and Dynamical Astronomy. This is a very important book on celestial mechanics, and for more information on the Kepler problem and the mathematical principles underlying celestial mechanics, you must consult Danby's book. And a very great 2-volume treatise is the book by Boccaletti and Pocacco. This book is advanced, but it is very comprehensive and a modern introduction to celestial mechanics. It's Theory of Orbits, Volume 1 and Volume 2. Now, what you could do is that you got a Kempton series involving Jn of n epsilon. You could try to expand the Bessel's function as a power series in epsilon and rearrange the whole thing and obtain a power series in the eccentricity. But the resulting power series will only converge when the eccentricity epsilon is less than 0.667. But the problem is that the orbits of most comets exceed this number. For example, the orbit of Halley's comet has eccentricity 0.96. It seems that an investigation into why this series fails to converge beyond this threshold led Cauchy to develop the theory of functions of a complex variable. There is an imaginary singularity that prevents the power series from converging beyond the threshold value. So power series cannot be used Kapton series or Fourier series is what needs to be used in this context. Thank you.